Hello everyone, so we're on page 37. We are going to talk today about similar solids, and this is actually us wrapping up three-dimensional shapes. We're done with volume and surface area and all that stuff after that, and normally now we'd start reviewing for the FSA, but we don't got that. So we're going to spend the next couple weeks just doing a couple things. Like I know trig was a rough chapter for us, so we're going to review some trig. And we are going to talk about factoring, because that's going to be important for those of you going on to Algebra 2 after this. So the next stuff should be some nice review stuff to kind of get us going. So talking about similar solids, just like when we had, like is supposed to be with an E. I don't know what I was doing there. Just like. With polygons, solids can be similar, right? Remember when we did polygons, we could say like, oh, this polygon, this square is a 2x2 square. Well, a similar square would be a 4x4 square. Or a rectangle, we could say this rectangle is 2x3. So a similar rectangle would be 4x6 because you multiply it by 2. That same thing can work in solids, but then when you compare it to their surface areas and their volumes, it causes things to be, hold on one sec. My sister is very rudely interrupting my recordings right now, so I will have to call her back. Okay, bye.
Bye.
Volumes and surface area have different proportional ratios. Okay, so let's take a look at this one here. Just first talk about how to determine similarity. You can see that I have these two trapezoidal prisms, right? And what I notice first is this top part right here. If you look right here, this part is 12 and this part is 3. So I could say, great, that means they have a 12:3 ratio. Since both those numbers are divisible by 3, I divided 12 and 3 by 3 to get 4/1. Done. Then I could compare it to their heights. You can see this one has a height of 8 and this one has a very small height of 2. So if that's the case, then you can compare that 8 to 2. Both those are divisible by 2. 8 divided by 2 is 4. 2 divided by 2 is 1. You got 4/1. Again, same exact thing. And then we could compare the bottom. If you look at the very bottom, yeah, green. I don't have a green open up for pens, though. There is a 20 and a 5. So we could make the ratio there that is 20 to 5. Both those are divisible by 5. And when you divide by 5, you get 4/1. So since all of those dimensions come out to a 4/1 ratio, then you know that those figures are similar, right? So when we take that further, though, and we're comparing surface area and volume, they aren't affected directly. They don't go in a direct relation with the proportion that you already have. If the ratio of the proportion was A to B, well, what's going to happen then is the surface area is going to be A squared to B squared, and the volume is going to be A cubed to B cubed. So if we use this one that we had in our example up here, if we use the proportions of the sides was 4:1. So we have a cube in which the smaller cube is a 1/1 cube, and then you have a bigger cube that has sides 4/4. So it's 4 times bigger. This cube is 4 times bigger. Well, when you look at that in terms of surface area, it's not going to be a surface area that's 4 times bigger, right? If you found the surface area of this little shape, well, 1 to 1 is easy, right? 1 times 1 is 1. And then there's 6 sides. So the surface area here would be 6. Where over here you have 4 times 4 is 16, and 16 times 6 would give us 96. So you could see those surface areas are very different from each other. And it's because what we're going to do is take this and square it. So the surface area has a ratio of 4 squared to 1 squared, which is 16 to 1. If you take 6 and multiply it by 16, you will get 96. The volume here, if you did the volume here, the volume of this cube is 1 times 1 times 1 is 1. Well, the volume here is 4 times 4 times 4, which is going to be 64. So your volumes are actually going to be at cubed. So you're going to take this original thing, 4 cubed to 1 cubed. Well, 4 cubed gives us 64. 1 cubed gives us 1. And you can see that it's a 1 to 64 ratio, which is what we expect up there. So that's how you find it. You always take your initial scale factor and square it to get surface area, and then take the initial and cube it to get the volume. So with that, let's look at our first example that we have. Sorry, that was loud. So our first example said, find the ratios given these two rectangular pyramids. And I know they're not the best drawings. I did my best. But you can see that the slant height here is 20. And the slant height here is 5. So I know that their scale factor is 20 to 5, which we could then simplify to 4 to 1. I literally just did that in the directions, didn't I? I didn't mean to do that, but I'm not going to redo it. We're going to leave it. So then we could do our surface area, which we just did. And we said we would take that 4 and we'd square it to that 1 and square it. So the surface area, let me finish writing, that would be 4 squared is 16. 1 squared is 1. And volume, I'm going quick because we already did it. That's not how you spell volume. Don't go quick because then you can't spell volume. Would be 4 cubed to 1 cubed, which gave us 64 to 1. So these are our values that I already accidentally did for you. So on our example, this is what I had. It kind of looks a little bit ugly, but that's what I wrote down. Pause that, copy it if you need it, but hopefully I already copied it because we kind of did it off on the side there. All right, my second example is this one. And this is our last example for this week. So cylinder A is similar to cylinder B. If the volume of cylinder A, so A has a volume that is 39 centimeters cubed, and the volume of B is 4,875 centimeters cubed, then how many times bigger is A than B? I meant to put B than A there. I'm sorry, that was my own mistake. How many times bigger is B, which is clearly bigger, than A? So we need to figure out how many times bigger B is than A. So without having any way to go backwards on this, you can't easily find the length of the size. But now that we know what the ratio is, we know volumes are cubed to each other, right? So what I'm actually going to do is I'm going to compare these two. What I'm going to start by saying is I'm going to take the bigger one and say, okay, well, how many times bigger is the volume of B to the volume of A? So I could easily do that. Take 4,875 and divide it by 39, and I get 125. So what that means to me is that if I take the volume of A and multiply it by 125, I'll get the volume of B. So B is 125 times bigger in its volume than A. But that's not its actual size, right? Because what we know then is that their volume is a 1 to 125 ratio. But this is cubed. This is A cubed to B cubed. So to undo that, you have to cube root all of it. So the cube root of 1, well, what are the 3 numbers that multiply to make 1? That's pretty easy. It's 1. The cube root of 125. If you don't know how to do these in your head, you could take in, you can look in your calculator. There should be a button in your calculator that looks like that. Find it somewhere on there. If you can't find it, the other way that you could do this is you could put it to the 1/3 power. You could put 125 to the power of 1/3, and those things mean the same thing. That's a little bit easier, I think, for some of you to do in your calculator. You can find that a little bit easier. But we take the cube root of 125. Well, the number that multiplies by itself 3 times to get 125 is 5, because 5 times 5 is 25, and 25 times another 5 is 125. So the cube root of 125 is 5, which means that B is actually 5 times bigger than A. Not 125 times bigger, even though their volume looks like that. It's 5 times bigger. So here would be this example written out a little bit neater. And that's it. There you have it for this week. So come see me at my office hours if you need help. I am here every single day, twice a day. Have a great week and good luck.